Thank you.
The floor is yours.
Yeah, so my name is Sherwin. I'm representing Sherwin here today. But thank you, Evan, and the rest of my collaborators on this project. So Harshal teed me up really nicely earlier with this talk about why methane emissions are important and some of the challenges in measuring methane emissions. My talk is going to be a little bit more about some empirical data and measurements from the Permian, specifically looking at some large reductions observed over a multi-year study from aerially visible methane emissions. So we'll dive in. So a brief outline of the talk today. I want to start first with the highlights, so to get you all oriented into what's interesting about this data, why it's exciting. Then I'll dive a little bit deeper and talk about why methane is important. Harshal kind of did everything that I needed to do with respect to that, so I'll go briefly through that a little more quickly. Then I'll talk a little bit more in detail about measurement and basin inventories, why that's important, and then we'll get into the meat of the presentation with respect to this actual multi-year data at basin scale in the Permian from 2020 to 2023. So highlights. I'll just define methane intensity really quickly. It represents the fractional loss of methane. That can be for an operator at the basin scale, whatever level of aggregation, but generally it's the methane emissions over the natural gas throughput from the system. And what we observe in this study across these 4 years is methane intensity is decreasing over time. But more interestingly, emission size distributions and the contribution of the very large emissions vary substantially, both across years a little bit, and also across different facility types. Midstream emissions, which I'll talk about a little bit, are a large fraction of total emissions, especially from the gathering lines and compressor stations in the midstream sector. And these large emissions are major contributors to overall emissions totals. I'll show you some good examples of those distributions. In the Permian, where all this data is from, aerially visible emissions alone amount to a large fractional loss rate. And I'll show a graphic that displays this, but even the lowest estimates from studies in this region are about 3 times EPA estimates from emission factors and greenhouse gas inventories. One thing that's interesting is even with increased scope of measurement, methane intensity is still trending downward. So over time, we're gathering more data, seeing more emissions, but we're still seeing this somewhat downward trend. And I really want to emphasize, I hope if anything is taken away from this talk today, it's that comprehensive survey with various technologies, including variable detection, is really essential to both characterize the contribution of different sizes of emissions and also figure out how to best mitigate them. So you saw this chart a little earlier. Thank you again to Dr. Kleinberg for putting this in one of their papers. Basically, what we're looking at here is why methane is important. It's a potent greenhouse gas. So we look at business as usual emissions, anthropogenic emissions of carbon dioxide and methane over a 20-year period and stop. What we see is that if we tackle methane emissions, we can see short-term benefits of that pretty quickly because the decay curve happens over a period of decades. And so even though the mass of methane being released is about 1% of CO2, the near-term temperature effects are comparable, and the long-term thermal effects we can see achieve better mitigation of this through tackling the methane portion of the problem. Again, one reason why this is an important problem to tackle is that there's a high climate impact potential focusing on methane specifically. We have a lot of levers and actionability in terms of tackling methane emissions from the fossil fuel sector, specifically the oil and gas industry. And oil and gas is responsible for a large portion of anthropogenic methane, give or take what the exact number is, but it's a large portion. And a lot of these emissions are fugitive, meaning they're avoidable. And there's a lot of resources and incentives that Harshal spoke to earlier with respect to federal grants and opportunities to invest in mitigating these emissions. Measurement is really key. If you look at U.S. greenhouse gas inventories, these are based off of measurements from facility to facility components, and these are expected emissions per year. But we also know that for measurement, that there are a lot of leaks, fugitive leaks, and these leaks are responsible for the majority of emissions coming from the oil and gas sector. These are really big sources, they're super impactful, but they're also rare. So it's important, speaking to what Harsha talked about earlier, the survey strategy, being careful about collecting a lot of data and measurements to find out where they are and characterize them appropriately so that we can understand their true impact. So basin inventories related, Harsha also showed this plot. What I want you to take away from this is that, again, different basins have different emissions profiles. There's different mixes of oil and gas production in these basins across the US and across the globe. And these also vary over time. So while we can assume some things about emissions within a given period, short window, we have to study these things continuously. We have to measure all the time and try to improve our sampling so that we can characterize them both geographically but also temporally. And one thing that's difficult in terms of reconciling both different basins, measurement studies, but also studies within the same basin is the fact that these different teams of researchers are using slightly different analytical methods, but they're also using different data coming from some of the things that Harsha described with respect to continuous monitors that are in situ devices, aerial emissions measurement, which is what we do at MIT24, and then a host of different satellite options. So I want to highlight a little bit more about the Permian, just a little bit. It's an extremely important basin. It's responsible for about 40% of oil and gas production in the United States. And if you were to treat it as a country, it would rank among the highest producing countries in the world if you were to treat it at that level. And it's been studied a lot. So we have a lot of good research to compare against in the Permian over a few different years and a few different sub-areas of the Permian. For example, there was Insight formerly Kairos, conducted a study in 2019 and found that there's about a 7.5% fractional loss rate from airily detectable emissions in the New Mexico portion of the basin. So that's that up to the upper left, the southeast portion of New Mexico. But obviously the Permian takes up a large part of western Texas as well. And you can see sort of a chart here at the bottom showing the distribution of wells across this extremely large area. I want to talk a little bit more about the actual technology here before I get into the data. So all of this data is collected with the Insight Leak Surveyor pod, which you can see a picture of it here, attached to a fixed-wing aircraft. And it's combined spectrometer, optical camera, and GPS system within this pod. And there's an example of a plume detection from the pod to the right. And one thing that's really important about not only this technology, but any technology looking to measure methane emissions is our ability to reliably understand its efficacy in terms of quantification and also seeing real emissions. So this pod has gone through 2 series of single blind controlled release tests. Most recent one in 2022, and it achieved a 90% probability of detection at 10 kilograms an hour. See that probability of detection curve on the left, on the right hand side of the slide, and a 0% false positive rate. So it's important to make sure that we understand that what we think we're seeing is real emissions and understand the error on our ability to actually quantify these rates. Again, I'll highlight I'm talking about aerially detectable emissions here. And while that's not the entire range of emission rates, in the Permian, we sort of estimate that that's about 80% of total emissions. So we're seeing a large majority of the emissions using an aerial sensor. One brief note about the analytical pipeline here. This is the same pipeline that comes from a Millennium Measurements paper, the Sherwin 2024 paper. I highly encourage you to take a look at that if you're interested. Essentially, how we're able to do this is we conduct massive aerial detection campaigns across the Permian, across multiple years. We have good data from third-party vendors about where actual sites are, pipelines, wells, compressor stations, so that we can actually associate an emission detection with a real site on the ground and understand what site and what segment in the value chain that belongs to. We gather statistics on coverages and detections. So when we actually see a plume and when we don't see a plume, which is equally as important, we perform the Monte Carlo simulations to come up with unbiased estimates of these emission distributions that Harsha talked about in detail. Importantly, we take that information from the single blind controlled release with respect to quantification error, and we bring that back in to our estimates to account for uncertainties. And then we finally end up with this product of estimates of total emissions and emissions distributions. So now into the fun part, which is the data. I'll call out, this is the largest ever time series of aerial surveys of the Permian Basin. We're covering 4 years worth of data here, and a lot of measurements. So if you look at the top row of this table, across all years, this is around 2 million measurements. So that's a plane physically flying over a real asset, measuring, trying to measure emissions or non-detections. To put that in context, other studies, are able to look at a few thousand emissions, maybe more than that, but nothing quite on the scale. So this is really exciting that we have both the temporal richness and also the spatial comprehensiveness of this study. And to that point, going down a little bit further in the table, looking at this yellow box, you can see over time we've been able to really capture quite a bit of productivity coverage. So it's really important that not only are we covering well sites, but we're also covering the whole distribution of production levels at these well sites. And even in the recent years, in 2022 and 2023, we're up to about 80 to 90% coverage of production, which is pretty exciting because that's as close to representative of the entire basin as we can get without absolutely flying everything. So we're getting into good territory here. And over time, as we've expanded the scope spatially and temporally, we're seeing more plume detections. So some of the results. This is a real example of those emission distributions that Harsha was talking about. This is all 4 years of the study on this graph. And to reference again, we're looking at total cumulative emissions fraction on the y-axis and emissions magnitude. So this is representing what portion of total emissions is coming from sites emitting at a rate of a certain size. So I put some reference lines on this chart. First, if you look at the one to the left vertically, this is around 100 kilograms an hour. So above this range is the territory of what we call these super emitters, these really large release events. And as you can see, a significant portion of this distribution is coming from total emissions in this aerially detectable range is coming from these large release events. Moving to the next line, vertically, is around 1,000 kilograms an hour. Still a very large contribution from these extremely large rates. And you can see there's some dynamics in terms of this long tail of the distribution on the right-hand side changing over time. Some of it decreasing and pulling to the left a little bit. And without getting too much into the weeds, to just highlight that there's a lot of opportunity to tackle methane intensity as total fractional loss by tackling these largest emissions. These super emitters are contributing a lot, as you can see, and that's remained consistent over time. So the better we can do to characterize them, we can strain our understanding of why they're happening and where they're happening, the better we can do to cut down on a large volume of emissions. So moving to looking at fractional loss, I often think of fractional loss and the contribution to methane intensity from well sites, and that's what you're seeing here. But well sites are only one part of the picture. If we expand this and blow it out, you can see that there's actually a massive contribution to methane emissions from other segments as well. One thing that's really interesting is the contribution from midstream, specifically pipelines, which Harsha also talked about earlier. And when we talk about pipelines here, we're mostly referencing gathering pipelines, which are the shorter length pipelines, which are taking product from the well site and bringing it to transmission lines or processing facilities. And we find consistently over time, there's a lot of emissions coming from these pipelines and also other midstream facilities like these gas processing plants. I'll briefly highlight these purple boxes on 2020 and 2021. You'll see that these are labeled as unknown. Really all it's chalked up to the fact that in historical data, we have an imperfect view into all sites in terms of their mapping across the space. We don't necessarily always know exactly where all sites are, not all of them are reported. But luckily over time, we've been able to do a better job of categorizing each of these sites where we're making detections and non-detections to be able to get a better picture of the contribution to this total fractional loss rate. And as the title of the talk says, you can see over time, even though we're expanding both in terms of space, what we're covering, and also just the number of measurements, we're seeing this slow decline in methane intensity. There could be a lot of reasons for that. I think that could probably be an entire talk on its own. I'm happy to discuss that further. I won't get too deep into that, but it is really interesting to see that as production trends change and also emissions mitigation efforts get deployed, since they're still fairly new, we are seeing in the Permian at least some slight decline in that methane intensity. Zooming in on 2023, I just want to call out some more numbers to emphasize the importance of this tail in the distribution. So specifically, again, looking at 10 to the third number, 1,000 kilograms an hour, at the contribution from different sites. So we see about 43% of total emissions is attributable to these large release events coming from compressor stations, 33% from processing plants, and so on for the complex well sites and pipelines. This is really exciting because, you know, if we only focus on one segment or part of the value chain, we're clearly missing out on some interesting dynamics that's going on in the other places. So for example, thinking about compressor stations, there are less compressor stations out there than well sites, so it'd be really interesting to dive into this data more and understand some of the root causes of why this is happening, and maybe why these large release events are occurring at a to a greater degree with that specific part of the segment. And really, in general, I hope you take away anything from this talk is that this breadth of data has not been collected before, and there are a ton of downstream analyses that we could do to dive in to these specific segments and piece out a little bit better why we're seeing such a varied contribution from these large release rates across different sites, but also sort of a consistent contribution over time and what those root causes are. I want to point out a quick sort of shortcoming or anomaly in this data. You can see that on this complex well site distribution, it sort of arcs out in a very extreme fashion towards the large end of the emission rate range. And I've put an image of this plume detection. It's an extremely large plumes, around 20 tons an hour in terms of its emission rate. And the effect we're seeing here is that we sampled this emission once. And so we're unable to constrain this ratio. I think this speaks a little bit to something that you asked Professor Kleinberg earlier, in the sense of, you know, if you're not able to uniformly cover sites a lot throughout a year, you get this sort of effect where, while we're still giving the assumption that this distribution is stationary, we're still capturing with relatively low uncertainty the actual picture of total emissions. We're not completely accurately characterizing the large emissions dynamics here in this particular case. And so this is just another emphasis that it's really important to get as much data as we can, both from early detectable sensors, satellites, continuous monitors, to try to piece together a better picture of what's going on across all bands of emission rates to improve our understanding of what's going on and the dynamics over time. So again, just circling back to the highlights here, methane intensity is increasing over time, as you see in the Permian across these 4 years. These emission size distributions consistently across time and across segments. We see a contribution from very large emission rates, but it is differentiated between segments and parts of the value chain. And again, just to hammer home, comprehensive surveying, both with area sensors like the one we have in InsideM, but also other sensors, and working to combine these measurements and reconcile them will help us really constrain what's going on, especially with these super emitters, which are extremely impactful for the overall fractional rates that we observe. And maybe just some food for thought to leave you all with. This is an exciting moment for the STEM. So this data is unprecedented in terms of its scope and scale. And we're now sort of at the cusp of a new opportunity with MERC, which is the Methane Emissions Reduction Program, which is a call to study and come up with these emissions inventories for all regions, producing regions in the United States. You can see color these different basins, Permian and green, and a whole list of other areas across the lower 48, and also Alaska. And this is really exciting because the methods and takeaways we have in this paper that we've been able to successfully apply across 4 years and across extremely large collection areas, I think can serve as a good grounding baseline and methodological reference for how we might go and approach collecting data at scale reliably with low uncertainty in the rest of the United States. And once we start to understand the nuances between these different basins and the specific contribution of large release events, we'll really be able to get into the details of how to effectively mitigate them with these various technologies. So thank you for your time. Happy to answer the questions.
One question. Okay, you certainly have given us the impression that 2 million visits is enough to characterize the Permian. I think that's not taking away from this. And first of all, is that true? And secondly, if so, do you have estimates for how many visits would be required for all the other basins? I mean, the Permian is exceptional. It's really, really big, really, really gassy. Other basins, not so much. So, do you have a table of how many visits you think would be fully characterizing these other basins?
It's a really good question. I don't think I have an exact answer for you, but I would say that yes, the Permian is uniquely leaky. So it definitely, well, and extremely large. So it takes, especially in these later years in the 2022, 2023 data, where we're able to cover the majority of production. That's really important. I think it's more a function of production representatives, particularly for well sites. Speaking to the survey strategy things that Harsha was talking about. Because as long as we can make sure we have a good stratified sampling across representative production, then we can, and we take a lot of measurements, ideally spaced out throughout the year. In some cases, maybe supported by follow-up from settlers or something like that. Then we can really do a good job of saying, you know, again, with the idea that we know that when we're not flying, there are emissions happening, but sort of capturing the total distribution is stationary. So I don't know if it'd be really interesting to think about that problem in terms of if there's a sort of golden number of measurements and what that would look like across different basins. I reckon it's probably a lot less to cover just because they're much smaller, they're less leaky. For example, like the Haynesville, Eagle Ford, I think it probably be easier to quantify them with low uncertainty, with less measurements, but certainly need to cover the production as well.
Practically important problem.
Yeah.
That, for example, the U.S. Congress would like to know.
Yeah.
How much money to appropriate to more or less solve the problem.
Yeah, absolutely.
That's the question.